6 o'clock. You've had a long day. I'm looking forward to talking with you about some of the passion I have about science teaching and learning more about how to teach effectively. And when I listen to, like, President of NARST, this is who I am. I'm a teacher. I'm a teacher. And I'm passionate about helping others teach in ways that are effective and learning from all of you. I've had a wonderful last 4 days with Umesh and able to visit a couple of schools. That was really a highlight. So I'll have a lot to reflect on. So this evening, my topic is one which is closely aligned to the next NARST conference topic. I was, as president, able to select the new topic for the 2018 conference, which happens to be in Atlanta, Georgia. And at that time, I was very emotional about things going on in the United States and also concerned. So the topic for this evening is how can we develop scientific literacy in young people in an era of science mistrust and misunderstanding. So I'm going to share a little bit of a philosophy with you and my personal passion, which I've already shared a little bit with you about. Talk a little bit of the state of science education in today's world, and talk about my ongoing research, which is towards creating environments for inquiry-based science teaching and learning and critical thinking, and hopefully have some time for future research. So I have a timer over there, and so if I get going too long, I want you to stop me because I want to hear from all of you too and have some conversation. So we're going to start off with this. I want you to look at this, and including you physicists, take a good look and make some observations. All right. Does anyone want to volunteer? What did you see? Do you have any questions about it? Yes?
I'm seeing a segmented organism. Most likely an invertebrate.
Oh, yeah.
With 3 pairs of legs.
Okay. So you clearly were carefully observing what was going on there. Now, do you have any questions about it? Does anyone have a question? Yes. Pardon? How big is it? Another question. Gentleman next to her. Sorry, I'm calling on you without you volunteering.
I was actually going to comment on that. By the looks of the focus, it looks like a very tiny insect.
Okay, it could be. So how big is it? What is it? We didn't have that question. All right, actually, this is an organism that is actually very small and was found here. This was my house when I lived at Cornell University. And this is snow, which we got basically every day for 6 months. And apparently these little things, they're very, very tiny. This was under a microscope. They're like a speck of pepper, and they're on the snow. And you pick them up. And my husband's a wildlife biologist, some of you know that, and he happened to see these specks, looked under the microscope, thought, oh my gosh, what is it that could live in -7 Celsius? How could that be, and what is it, of course? And so this is an example of scale and asking questions. And for me, this is an illustration of what we do in everyday life, which is question and inquiry. So I do have a passion about teaching and learning science personally. As a science educator, teacher educator, researcher, and former classroom teacher teaching, I'm not satisfied with the way that most science is taught in most schools in the United States. Now, I've only gone to two schools in South Africa, but each time I talk with esteemed researchers about our common issues, common problems, I think we have more alike than different. So I'm passionate about helping teachers move from using a direct teaching approach, mainly focused on memorizing definitions of scientific terminology, toward a more student-centered and rich and investigative experience using logic and evidence. Now, as was mentioned, I am the current, as of 3 weeks ago, president of NARST, and I would love to see some of you in Atlanta. It's in my own backyard, and there you'll see the Olympic torch, or a replica, and you can see the cityscape there of Atlanta, and we have an aquarium. And NARST is the worldwide organization. We also have some natural gorges. And that stone mountain is very interesting because it's very tied to culture. It's just this stone piece of rock that many cultures have come to gather by. It's called Stone Mountain. And the theme, and here's the Center for Civil and founded by, in respect for Martin Luther King, and also there you can see the cityscape. So here's the theme: recentering on scientific literacy in an era of science mistrust and misunderstanding. So in today's social context, we have disturbing trends of anti-science rhetoric in my country. Scientific literacy as understanding concepts and principles of science and how scientists use logic and evidence. That's how I'm framing scientific literacy. So a two-pronged definition. One is obviously the concepts and principles of science in addition to the use of logic and evidence, and that is a very important addition. Also, we're concerned in the United States about the achievement of all populations of students, especially those that are generally underrepresented in the sciences. So there's the theme, the new theme for NARST. And some of it relates to environmental crises that we're having now, where we need informed citizens to make personal decisions based on scientific evidence. And I don't know how it is in South Africa, but in the United States, we have some people who are very tied to their religion and are afraid of embracing theories of science, such as the theory of evolution by natural selection. And I articulated these bulleted points about anti-science rhetoric, the discounting of scientific evidence, and potentially undermining concepts such as evolution and climate change. So, I don't have any answers, really, this evening. I have some ideas for my own research and for my own passion, but I always go to education as our fallback. Education has got to be the key to developing informed and logical and passionate citizens. And education comes from passionate teachers. So I am proud to be a teacher, and those of you who are here in the room, can you just raise your hand if you are a teacher? Yes. And professors, you are teachers as well. Some of you aren't raising your hands. But yes, I am respectful, too, of the challenges of teachers in today's world. So we have a new administration in the United States. You might have heard of him. Yes, and I have been watching CNN since I've been here in Johannesburg. And it's depressing in some cases and shocking. I have a son who's a mechanical engineer, works for the EPA, and the new head of the EPA has taken down the website of EPA. Teachers can no longer access lesson plans on rising sea level in the United States. That's a concern. Devin Powell is a writer of Scientific American, called me up a couple months ago and asked my prediction for the first 100 days for Donald Trump in education. And I said, well, I don't think there's really, it doesn't sound good, let me just say that, because there has been no evidence that the support for public schools is there, the support for the environment, teaching about climate change and evolution. So it is still yet to be seen. And there it is about the EPA tearing down the website. They're going to reconstruct the website under the new administration. So changing some scientific findings and refashioning them. So again, there's a critical need in the United States and other countries to prepare teachers in STEM disciplines and knowing how to enhance achievement of young African Americans, Latino, and other students from populations generally underrepresented in the sciences. And so I don't know, there's a block of teachers up there, right? I don't know if you come across this, but sometimes students don't have motivation. They just simply aren't motivated. So that's a huge problem that my new teachers deal with, the lack of motivation. So if you have a lack of motivation in students, in especially the younger ages of 10, 11, and 12, then obviously they're going to opt out from taking mathematics and science. So this is a concern. Also, there's research to show that many teachers do not embrace the kinds of teaching that is supported by research to motivate students or to engage them in deep understanding of science concepts. 60% of teachers self-reported reform-based teaching. Now, maybe you think this is good because it's over half. I think 40% don't, and I'm not convinced that self-reporting is valid. So, some of the research I've done with my colleague Dan Capps is that it is rare to find teachers who teach in a way that is a little bit less traditional, less comfortable, and it's frankly very difficult, the kind of teaching that we're going to talk about this evening. In the United States, there has been an emphasis on teaching science as inquiry in the classroom. However, many people don't really understand it. And so we have a new document called the Next Generation Science Standards. And there is highlighting there engaging in science practices, but also about the nature of science, which I will always also talk about this evening. I know from Umesh sharing your CAPS document that South Africa, this is music to my ears, you also in South Africa are advocating active and critical learning and active and critical approach to learning. So rather than rote and uncritical learning of given truths. Also, you hope that your students will have scientific skills and ways of thinking scientifically, so that in the popular media, a student can be critical of the media, critical consumer of web-based information, and be able to, at the same time, talk about the biological processes and concepts and investigations according to life science. So I've done a series of investigations over the last 22 years focused on various aspects of teaching sciences inquiry, starting with that study, which was my dissertation. I did a very painful dissertation. It was on my own teaching. I had to look at myself. I had to videotape myself, go dissect the videotape, come back the next day, be brave enough to teach again. I cannot tell you how much respect I have for teachers who actually allow someone to videotape her and then analyze your teaching. But I learned a lot about my students in my class and how I could motivate them to collaborate around projects. Some of the other studies that are built upon there involve a teacher in the Pacific Northwest who used inquiry-based practices. Recently, I wrote a chapter in the new handbook on inquiry, and I titled it From Inquiry to Scientific Practices, because in the United States, in the new document, inquiry appears 2 times in the entire document. Of course, for a researcher who has built her career and life and passion on inquiry, to see the word inquiry 2 times in the new document was a bit concerning. However, the reason is we wanted to really define what inquiry was related to specific science practices. I know some of you are scientists in the room, so you can relate to this. So again, the confusion about the meaning of inquiry is a concern to the United States. My definition of inquiry is this, and I apologize for it being long, but I needed to include quite a bit of the practices in the definition. So what it means is to engage students in using critical thinking skills that includes asking questions, designing and carrying out investigations, interpreting data as evidence, creating arguments, building models, communicating findings. And the bottom part there is, for me, so important. So again, use of logic and evidence about the natural world. So that is what I hope to help, and myself as a teacher, embrace. Here are the science and engineering practices in the United States that relate to inquiry. And here are the ones that I think are the most difficult. So, how do we help our young children in science classrooms to define problems in engineering? We have the engineering practices too. How do we help our young children develop and use models, interpret data, construct explanations, and engage in argument from evidence? For me, and I help my young teachers think about this, it's overwhelming in a sense. And if you just think about this, think about that segmented, crawly little thing that you saw earlier in the lecture. We talked about data. It's just about making observations and grappling with the data to use logic and evidence. So for me, inquiry has to have some kind of data in the teaching, doing something with data, dealing with data. So, assumptions. How can we have students understand what science as inquiry is if they don't experience it themselves? So, in other words, we have to change the roles of teachers and the roles of students. That's the other thing. I'm just going to get some water. That I think is important, because if you've been in a traditional classroom lately, or if you've been in a college lecture hall, sometimes students are passive. And it takes energy to be active, an active thinker. So we can't just change the roles of teachers. We have to encourage students to also change the role of the student, to be more active and work hard. In fact, when I was teaching chemistry, we were doing a project based on chemicals in our lives. And we had investigations going. I was trying to teach the concepts of chemistry through the project. And at one point, some of my really good students said to me, Mrs. Crawford, can't we just have a test over the periodic table? Can't we just memorize the symbols? And that is, okay, we're going to get to that in another week, but it hurts your head to think in the ways that we think people should think. So why don't we see this more? Why don't we see this kind of teaching more in classrooms? First of all, we don't all agree on what it is or what it should be. The other thing is we don't have a lot of empirical research on effective teacher education programs. We also don't have a lot of research on classrooms with diverse students in classrooms, either culturally, racially, or by language. So teachers say this, I don't have enough time. And this is in the literature, lack of time. Well, that's all of our problems, right? It's like time. It's a challenge of turning questions back to students. That's key in inquiry. What kind of question am I going to ask a student once that student asks me? Instead of answering it, turn the question back. Too much to teach. Classroom management. My students are going to go crazy. It's going to be chaos. Inadequate space, inadequate time, large classes, and this one. My principal won't let me teach this way. So based on the literature, we know that in order to support teachers, based on previous literature, in order for a teacher to teach in this way, the teacher needs to know a lot about content knowledge, have experience in inquiry as a learner, have the curriculum materials that help one teach in this way, reflect on one's own practice, and have support in the classroom. So if we have these 5 components in some of our programs, hopefully that will help support teachers. So one of my projects involved using fossils to help teachers teach students about evolution. And for me, it's extremely important that in learning and understanding evolution by natural selection, that you have an appreciation of what science is, the nature of science. And I was fortunate to collaborate with 2 paleontologists. Both of these paleontologists studied with Stephen Jay Gould, and both were passionate about teaching. So the basis of the project was it was situated in New York State where there were a lot of rock. There was a lot of rock and a lot of sedimentary rock. And the question was, we knew from dating that this rock was 380 million years old. That was just like inconceivable for me. Deep time is so hard to think about. And the question the scientists came up with was, how do the organisms that were preserved and fossilized in this rock respond to the changes over time? How do the organisms respond? So as educational researchers, what we wanted to do was to create a real context for students to experience what science is. At the same time, we wanted to motivate the children. And we wanted to motivate these children who are in ages 10 through 16. We also knew that we needed to develop educational materials because we can't expect teachers just to create wonderful, innovative materials. There's not enough time. So according to NGSS, the core concepts we were trying to teach were about biological evolution and answering the questions, how do organisms change over time in response to the change in the environment? This is the same question that evolutionary biologists have now and the climate change scientists have now. The best evidence for evolution are fossils. And so that's the best way to provide students a chance to think about the evidence that relates to the scientific evolutionary theory. So we developed a collaborative model. This came out of the project. And I have a vision that it's important for scientists and science teachers and students and educators to work together. So the way the study went is that the rock along the road right there, this is a really busy road, and in fact you could get killed on that road. Therefore, we couldn't really bring students. The teachers collected the samples of the rock, and then we shipped them to the classroom. We had about 30 teachers over a period of 7 years. These are the students in the classroom. These are teachers collecting the fossil rock. These teachers did not know much about the fossils. Many of the teachers were very worried that they would be expected to have the students identify fossils that they didn't know. So part of what we needed to do is work together to assure the teachers that they understood how to identify the fossils. And here's a classroom here in which that's what they're doing. All of these teachers volunteered. So they are all teachers who wanted to teach in a way that may be different than what they were teaching. And I have great admiration for them because I know it's a risk to teach something that you haven't taught before and you're a little bit worried about it. But these are some of the organisms. Crinoids, this is a trilobite. Now this is a specimen organism. It wasn't like this popped out of the rock and students said, wow, look at this. These fossils were hard to see, just trace pieces of shells and so forth. The idea was to create a model of what the environment looked like, much as a museum paleontologist would. Again, this was the environment where the rock came from. Now if you look at that, what do you think the environment would be for the organisms that were preserved in those fossils? Yes.
It should have been wet.
It should have been?
Wet.
You think so? Why is that?
Oh, you time to sort of settle down.
Oh, you're thinking about, you know something about sedimentary rock, right? Yes. So you're using your prior knowledge to figure that out. But if we asked a student, what's the environment like? They might just say dry, hot, grassy, because that's what they see. But in fact, when you look at the fossils, there are shells in them, and then you can infer it's got to have changed. It looks like it used to be an ocean. So in our model, the first phase is to engage the teachers as a learner and learning about the science, learning about the pedagogy. And then in the same way, they engage their students. So they came to upstate New York for basically 6 days. That was it. and they stayed all day, and they stayed overnight, and took them out to the rock, and they learned about the fossils. We engaged them in lessons in which they would teach their own students. And then they went back to the classroom the following year and taught. The next summer, we brought them back because we realized that, because we went into the classroom, the teachers were teaching the lessons excellently. However, the teachers themselves did not really get the fact that science can be very messy, that a scientific investigation doesn't start with a question and linearly goes to the end. So we thought we're going to have to get them to experience the science themselves. And so we asked these groups of teachers to go out and you design an investigation yourself, answering a question about these organisms. And then the next year we brought them back again and had them critically reflect on their teaching. And they became knowledge producers for other teachers by writing articles. Now, I'm giving you this model because the model emerged from the project. And my question to all of you, and I want you to think about this, I'm going to talk to Umesh, is the model relies on scientists working with teachers and science educators. So how can we, this is a pretty cool project, do you think? Does it sound like it? Would you like to go and spend, I liked it, but we can't do that with all teachers. What can we do in order to immerse teachers in experiencing this kind of thinking? What other surrogate experiences can we have for teachers that is similar to how scientists work, but maybe not exactly in the laboratory, not out in upstate New York? I would love to have you all come with me upstate New York, but we can't do it. It's not feasible. So I just want to put that question out there because we might be returning to it. So these are the fossils. And these are the children in the classroom. And this is the data sheet they had to fill out. They had to measure the fossils. And it's pretty cool because you can make inferences about the environment based on the color of the rock. So the darker the rock, the less the oxygen. That gives you a metric for the environment as well. The bigger the parts of the shells could be more nutrients. So it's a matter of statistics. We were trying to find all the fossils in the stratigraphy of the rock. And as you know from your own intuition, where are the oldest parts of the rock? Is it at the bottom or is it at the top? At the bottom. That's a scientific principle of superposition. So that's what we taught the students as well. So we were trying to figure out if there was a change of the organisms over those strata by looking at the data. So I'm going to move along because I see my time is going. What we did with the computer software is to make it easy for the students who maybe were 10 years old to count up the fossils, and then we would have frequency pie charts. And what you can see here is a lot of data over that height of the road. Does this make sense? Don't you hate that when teachers ask you that? Does this make sense? If it doesn't, you're thinking, no, it doesn't. But these are the different pie charts, and this is the frequency of certain taxa of fossils. And you can see that, for example, this kind of fossil now is more frequent. And just that simple of an inference is powerful if you think about how do scientists know about the changes over time. I'm going to go through these slides. So we did research on, are the teachers learning? Are the students learning? How can we systematically assess teachers? And do they actually translate their views into the classroom? So we had data across 4 areas. One is their views and subject matter knowledge. We gave them a test, pre and post. Do they intend to act on their views? What do they do in their classroom? So it would go into the classroom and videotape. And then ultimately, this is the only thing that matters, is do their students learn? So we had a group of teachers who were teaching in the same school as our project teachers. And we also pre-post test those teachers and their students. So we could have a quasi-experimental design. And we do have evidence of the teachers learning in comparison to the other teachers. Now you may think, well, it is significant. It's not huge, but it's definitely significant. Their views of nature as science were enhanced, as well as simply knowing about the geology, principles of geology in comparison to other teachers. So we had to collect data on that. We also interviewed the teachers about their views of what inquiry is. And I won't read all of that right now, but basically, some of the teachers believe that inquiry-based teaching was like, let it go. Just have students explore on their own. Just put out the materials. However, we know that the teacher has an important role of scaffolding the students. And so throughout the project, we were hoping the teachers would gain a more robust understanding of the tremendous role of the teacher in knowing what kinds of questions to ask, how to scaffold the students in each case. So in this pre-post view, the teacher said, and also moving forward as you become a teacher, would you like any professional development on science practices, and what would that look like? Became science's inquiry is that it should be taught through meaningful learning experiences. First, the students need to be engaged. We're not lecturing the kids or giving them the right answer. So we have qualitative analysis of video from the classroom in which we can interpret and infer that the students appear to be motivated. For example, I'm going to show you a video clip of one of our teachers who at the beginning had no idea what a brachiopod was. That was one of the fossils. Or a bivalve. And those are 2 very similar fossils. She taught students that did not speak English, who did not speak English. And she's very brave. She was wonderful to put herself out there and let herself be videotaped. So what I want you to see is what is going on here. What is the teacher doing?
Trilobite, let's see. What do you think it is? Okay, see, look at the trilobite and see if you see any differences between this and that. You don't see any differences? How many sections does this have? Well, right here, go across. How many sections do you see? Right here. Right here. Yeah, this is a section, this is a section, this is a section. There's 3. This is split by like, kind of like a backbone or something here, what kind of looks like? That's split in the middle. So we see that there. You see 3 sections? Okay. And if this was the middle of the trilobite, look at it. Right. So now, what does that look closer to? Okay, sentiment stems, or what do they call? Crinoids. That looks more like a crinoid. So that's baby final. What do you think that might be? Very interesting. Good job, Ricardo. Let's
So that is a non-traditional teaching experience in my view, because what was actually going on during that episode? Can anyone describe it? Was the teacher telling the answer? At any point, almost not.
Yeah, she was actually probing the learner.
Yes.
To the right answer.
Yes. It was a series of questions back and forth, trying to guide the students. In the next video, you'll see another one of our teachers who, again, the first time he's been helping the students understand the differences. And this is, what's going on here is the teacher gave groups of students different samples of rock. And they found the fossils, made some, there's no technology involved here, made some bar graphs of each of the 3 sections of the road.
So we can start drawing comparisons and saying, about the same number of brachiopods and clams in that part of the rock. And there's more brachiopods than clams in this part of the rock. And in that sample, there were more clams and brachiopods as well. We can start drawing comparisons, seeing what's the same and what's different about the different samples. Why do you think it's important? Why might it be important for us to know that there were more brachiopods than clams in this sample than there were in that sample? And I'll give you a hint. These samples came from the same location.
So you may look at that video and say, well, the teacher's doing all the talking. However, the kinds of hopefully ideas he's asking the students to think about will lead them toward comparing the data. And the last videotape is a 7th grade student who is trying to interpret the pie graphs to make sense of them. This video does not work. By the way, notice in the other classroom there was no technology, and here I'm using technology, it's not working. So this is a perfect example of you don't need technology to teach. If you heard the video, he would be explaining the inferences about the different environments for the different populations. So we do have evidence of student learning in comparison to the other classrooms. The students that engaged in the investigation learn more, significantly more, than the comparison students about the subject matter and about nature of science. So what do we learn from all this? This is a lot of text, but it's kind of a lot of my thinking about what do we need to do to support teachers. We believe teachers need to have a deep and integrative knowledge of foundational science concepts. You can't get away from it. You can't also keep saying, I don't know, I don't know, I don't know. Some people will say, it's okay to say no, but if you know nothing, you know, your students are going to lose confidence and you're not going to be able to scaffold them. The other thing is so important to understand what science is, the nature of science, as well as being reflective about your own teaching. In order to expertly support students in scientific practices, inquiry, use of logic, and critical thinking. So we need to give teachers ample opportunity to experience authentic scientific inquiry somehow, similar to how they're going to engage their students. And teachers need time to reconsider their views. So here is one model I put up, and I know I'm kind of running out of time because it's almost 6 o'clock already. I'm having a lot of fun because I'm teaching. You're sitting there. It's more fun to teach. But this is the model that I've been working with. And what I would like to think about is how we can engage teachers as a learner here, first of all, in the pedagogy, but right here in thinking about science. How do we engage teachers in thinking about science? So, what knowledge do teachers need? They have to know the subject matter, and they have to know what science is. I believe, this is my beliefs and from my research, and how to carry out this kind of teaching, and to have experience. I'm going to run through some of these quickly. I want to thank my collaborators. I have a lot of collaborators. The Inquiry Lab members keep kind of growing. Kayla is a first-year doctoral student, just beginning to think about this. Ben Campbell has graduated and has a job. So over the period of looking at the data, once a week we meet together grappling with what does it mean to teach science as inquiry. It takes a lot of resources. It takes an understanding about how to reason. And if we just create policy documents with no support to teachers, it's not going to change anything. And if we want to rebrand science practices to make it look different than inquiry, it may or may not do anything either. So here are a few questions for you all. And then I will go to my colleague. How can, this is the question I keep struggling with. How can teachers teach about authentic science practices if they have not experienced them? In my own teacher preparation program at the University of Georgia, we have our students for 1 year. They go into the classroom for half of that year, and I teach a seminar during that time. But the first part of that first year, they learn about methods, writing lesson plans, classroom management, multicultural education, and then they go in to teach, and then they're out the door. Where have they experienced this kind of learning and thinking? How can we create partnerships with scientists and teachers and science educators? And how can we help all children in classrooms that may not have the opportunities of other children? What about, I know this is probably not a very politically correct question to ask of people who teach lecture courses, but how can we redesign undergraduate science courses to help prospective teachers understand scientific inquiry nature of science? So there are some questions. I would love to hear the answers. And I got more to talk about, so